Okay, now that we've taken a look at a couple of examples of rotations, let's actually walk through the algorithm. This is from another textbook previously used in this course. And so, first of all, here is what the struct looks like. You'll notice that it has an element of type comparable, and the left and right pointers, and then the actual height of the particular node. And it's got two constructors, one for L values and one for R values. Okay, so it's got a copy constructor and a move constructor. And this is more than likely a template. So comparable is would be a type parameter. And it basically just means that in this particular implementation, there is a less than and is equal to operator overload in the actual class that you will be using this with. So you could actually use this with, say, objects of the gas pump class and insert those into an AVL tree. Here is the height function. Returns -1 if the pointer is null, and otherwise it returns the height of the height of that particular subtree, which is stored in the height data member here. And finally, let's look at the insert function. The insert function is a recursive function that takes a comparable element and then an actual node. And you notice that it calls itself in two instances. It calls itself with the pointer to the left subtree if the comparable is less than the element at this particular node. So we're at node T and we're comparing this particular value. And so if X is less than what's in the node's element data member, i.e. right here, then it's going to call insert with the left subtree. Otherwise, it will call it with the right subtree. If the pointer is null, it basically creates the node and it would attach it at that specific point. Okay, because T is the pointer that's coming in, and if T is null, well, the pointer is already there, so we just create a new node and we attach it to the pointer. So T equals new AVL node. Now, this call to the balance function at the bottom, this is what ensures that balancing happens at the lowest level in the tree. So I'll show you an example here with just an abstract tree in a second. But hopefully you can see that at some point when I exit this if statement, then I will actually invoke the balance function. So we'll look at that in a little bit more detail. Let's take a look at the node deletion and removal. You'll notice that this is also a recursive function that takes the comparable, i.e. the value that I want to extract, remove from the tree, and a node pointer, okay, an AVL node pointer, and it goes through and actually removes the item. And then you notice that it also, like insert, rebalances the tree, and this ensures again that this rebalancing takes place at the lowest possible point of an imbalance in the tree. Okay, so it recursively calls itself here and here, and then it handles the deletion of a node with two children. In this case, it actually substitutes the leftmost node in the right subtree, and then dives further into the tree to remove that node. You'll remember that when we delete by copying, we don't actually delete the node that we say we're quote unquote deleting. We delete a node that's either the leftmost in the right subtree or the rightmost in the left subtree. The else clause will handle the deletion of nodes with either 0 or 1 children, and those are the three cases, and therefore once we exit this particular if with all these else's, we will then rebalance the node. So what does this magical balance function look like? Let's take a look at that. Okay, so this is the balance function, and I've annotated some things here to help us go through it. But first of all, you'll notice that in this particular instance, they actually allow you to set the imbalance. The AVL definition says that if the imbalance is 1 or more, then the node has to be rebalanced. But this particular implementation allows you to change that to 2, 3, 4, or whatever else you would like. Right, so the balance factor actually checks two things. It checks if the tree on the left side is heavy or if the tree on the right side is heavy. So this is from the perspective of node T. And so if T's left is what's heavy, that's still not enough information to figure out what to do to fix this heaviness. We have to know whether the heaviness occurred in the left child of T's left child, or whether the else clause in the right child of T's left child. Right, so this is right of left child. And these two cases are symmetric. So basically what we're saying is that if we're left heavy and the left subtree is what's heavy, the left subtree of the left child is what's heavy, then we know we need a single rotation with the left child. This is an example of an outer case. For instance, something like this. Okay? We're saying if this is the heavy tree and not this one, then this is an outer case. Otherwise, if we had a situation like this, where this was the heavy tree, right? So the tree is left heavy. This is T here, and this is T. So from the perspective of T, in both of these cases, T's left child is what's heavy, right? So let's fill this in with T's right child here. Okay, so T's left child is what's heavy. In this case, it's the left of the left, so it's an outer case. In this case, it's the right of the left child that's heavy. And so this will require a single rotation, whereas this one will require 2 rotations. Right, the first one being this one. Okay, so these two cases are simply symmetric cases of the same thing. This establishes the very same factor for right heavy trees, and so we want to know if it's right heavy, then we want to know if that heaviness came from the right subtree of the right child, and if that's the case, then it's a single rotation with the heavy child. So it's a outer case. Otherwise, it's a double rotation with that child.